So this is the second lecture of the guest lecture series, which is organized by the Astronomical Society of University of Peradeniya for the year 2020-21. So first of all, I would like to welcome our guest speaker, Mr. Janaka Adassuriya, who's a senior research scientist of Arthur C. Clarke Institute for Modern Technologies. Next, I would like to welcome our head of the department, Dr. Varuni Senaviratna, as well as the senior treasurer of the Astronomical Society, Dr. T.P. Ranavaka, and all the lecturers from Faculty of Science. Next, I would like to welcome all the temporary staff members and all the undergraduate of Faculty of Science. So without further ado, I would like to invite Mr. Janaka Adassuriya to continue his lecture. Thank you. Sir.
Yes. Can you hear me?
Yes, sir.
Okay. Good afternoon to everybody. And so it's I first of all I would like to wish a very happy as well as a healthy New Year 2021 to all of you. So it's nice to have a presentation again through this series. This is the second presentation in this series. So we discussed about earlier about history of astronomy, and then so this is the second one, and we are looking for solar system objects. So that means the solar system we will discuss it in detail. We're supposed to discuss it in detail. Uh, so it's a very long session. If we go for the entire solar system and then all the objects individually. So therefore, we thought to start from the objects that is the most important thing of the solar system, that is the sun. So the today's lecture is sun as a star. I would like to discuss about some information about the sun, about the function and then the characteristic of sun. So because now this is important uh, because that is just a one star. Sun is a just a one star, even that is a small size compared to the other stars in the universe. So it's important to learn about this star because because of the sun. Actually, we are living here. The solar system is there because of the sun, and we are getting the energy and we are getting all the support from the sun. So actually, what we why we live here, that is because of the sun. So that's why basically we would like to have in detail about the solar activities and the properties of the sun in this presentation. So let me share the presentation with you. Okay, can you see the slides? Can you see the first slide?
Yes, sir.
Okay, so this is the topic what we are looking for today: sun as a star. So let me briefly discuss what is the importance of studying or just looking at this object, because there are a lot of objects. If you take different objects in the universe, so basically the universe is actually made out of stars, or it is rather made out of galaxies, set of stars. But if you go for the individual object or individual the building block of the universe, actually it's a basically it's a star, right? So therefore, it is very important to learn about the stars, right? So why it is important? Why we study the sun? So we can see that there are different uh, points we can actually point it out why we study the sun. So first of all, we can think about the influence of the sun to us, right? Basically, the influence means the how the sun actually varies, right? And then how it is going to affect to the Earth system and all these things. So therefore, we can actually discuss about the climate connection. Climate connection is directly how the sun actually connected to our climate. That is the direct impact. Of course, now we know that the sunshine is there and it is always actually uh, constant at the moment. We don't see any variation of the sunshine, right? Or the luminosity of the sun, it's almost same. But apart from that, there are some activities sometimes actually influencing the earth system. That means the earth and sun environment. In between that, the earth sun environment, so it's affecting by the solar activity. So that is what we learn as a climatic connection, right? The quantity and the quality of the light from the sun varies on time scale from milliseconds to billions of years. So we learned about in the early lecture also, that is the sun actually took a long time to actually come to this present condition. So then therefore uh, the variation of the light, or maybe let's say the radiation, is actually changing from time scale to milliseconds to billions of years. So it's a large scale variations as well as a short time variations are also there. So therefore, it is important to learn about these variations. The sun is a source of light and heat for the life of the earth. Of course, it is well known thing. I mean, we are living here because of the sun. These variations are unaffected. Uh, sorry, are affected our climate, but in uncertain ways. So that is the uncertain ways is the important thing, because we know that there are variations, but we don't know when it is going to happen, these variations. So sometimes very short time variations, whether it is going to be like a 1 day or maybe 2 days or maybe within 1 hour or 2 hours. So maybe a long time variations, how these variations are there, any connection or periodic changes are there. So there are a lot of things we have to look at. So that's the importance of studying about the sun. And space weather. So the space weather is basically, this is the climatic connection we call, that is a climatic connection. And we have to look at the space weather. Uh, the basically the space weather is governed by the sun. Now we have the weather, that is the local weather is governed by the earth atmosphere. It's controlled by the earth atmosphere. But the space weather is fully controlled by the activities of the sun. So therefore, we have to look at the space weather in detail. And the sun is the source of the solar wind. Now we know that there are a lot of activities of the sun. So it is a source of all these solar winds, solar flares, energetic particles, and all these coronal mass ejections. You might heard about these events. A flow of gases from the sun that streams past the earth at speed of more than 500 kilometers per second. So you can imagine how fast these particle streams. So most of these particle events, uh, these particle events actually flowing through the entire solar system. So it just passed through the Earth system as well, with a very high speeds, like 500 kilometers per second. So they are very high energetic particle events. So it is completely then change the space weather. The space weather can change orbits of the satellites and shorten mission lifetimes. So we have a lot of problems with this solar activities. So there are some incidences actually reported, missing satellites, shortened mission lifetimes, and all these things due to the solar activities. Shaking Earth's magnetic field can also cause current surge in power lines that destroy equipments and knock out power over large areas. So I will show you one incident later on this presentation. So some blackouts, the complete power blackouts also actually we had experience in some countries due to these solar activities. So in that way, it is important to learn about these solar activities, the behavior of the sun in detail. So that is about from the side of space weather. So then we can actually study the sun as a star. So we know that the sun also serves important role in helping us to understand the rest of the stars in the universe. In that way also it's important because that is the closest star to us, that we can reach it at least. We can actually look at it very closely. Basically the outside as well as the most important thing is the inside, what's going on inside the star or inside the sun. So that means we can get some idea about how a star actually just evolved during the time and what are the changes which happens inside that. So those are the things we can learn when you look at the sun. So it is important to uh, get some idea about the other stars as well in the universe. Sun as a physical laboratory, right? Of course, that is uh, the most complex physical laboratory, the natural physical laboratory in the universe. It's a very dynamic as well as it's a very complex. We could not understand the fully could not understand, or we do not understand what is going on inside the sun. Some of the processes, even some physics, it's not really clearly known inside the sun, inside the star. So therefore, when you look at as a physical laboratory, right, a natural physical laboratory, so it will just provide a lot of information and will update our physics what we learn today, and there are a lot of advantages, right? So basically, when you look at the sun, uh, the basic statistics I have listed here, like mean distance from the Earth, one astronomical unit. You know the astronomical unit is one unit we may use it in astronomy. It's a very long unit because a kilometer is a very small unit. So it is almost 150 million kilometers, one astronomical unit. That is a Earth Sun distance. And if you take the mass in with respect to the Earth, that is this much of mass, right? And then the mass in grams, it is about 10 to the power 33 grams. Equatorial radius, 695,000 kilometers. In terms of Earth radius, then that is 109 times of Earth. Mean density 1.4, that is if you take in terms of again Earth. Rotation period, the rotation period is an important thing here. Now you can see uh, this rotation period is important. uh, Now it is not a constant value. It is 25 to 36 days. Now we have a very uh, uh, a, a constant value, that is 24 hours, right? One day for Earth, but rotation period for Sun is 25 to 36 days. So you know that that is a gas giant or gas ball. So therefore it does not need to rotate all these layers like equator and then the pole. So they those layers do not need rotate the same way, same rate. So usually what's going on there, the equator, the layers, they close to the equator, those layers actually move faster than the polar regions. So the polar regions actually just take maybe like 36 days, and the equator rotates a little faster, like 25 days. So we call this rotation is called a differential rotation. Differential rotation. So it is a common for any gas object. For rigid object, you know that it's going to be same, like every if all the places actually rotate with the same angular velocity. But here it does not need. So this will be actually a reason. Later on I will come to this one. This Because of this, there are some solar activities appear in the sun. So I will come to that. But remember, differential rotation is important in solar activities. Escape velocity, it is a huge object, so it's a very high, 618 kilometers per second. But this is Earth system. Do you know what is their value for Earth system? It's 11 kilometers per second, right? It's around 11 kilometers here, 618 kilometers per second. And the luminosity is the energy release per second, energy release per second. So now the sun actually emits almost a constant energy per second at the moment. I mean, when you consider about slight changes, I mean, we don't experience it very high changes like overall, right? You don't see any much difference per second. It's almost constant. Magnitude means this is the how do you look at the stars in the night. So we need a scale to express their brightnesses. So when you go to this scale, that's called magnitude scale. You know that is the sun is the brightest star or the object in the sky, day or night time, right? Brightest object in the sky. So this magnitude scale is actually it's the negative minus 26.8. The minus means more brighter. So that is bright objects, right? The negative side means a bright, and then it goes to the positive through the zero, and then it's going to be weaker or maybe faint objects. So more plus means faint, more minus means bright. So that is the idea. Mean surface temperature. The surface temperature is 5,700 K. So our sun is a G-type star, right? In the spectral order, you know that the spectral order we can actually classify a star according to the temperature. So very high stars like maybe 30,000 K, they are called O, and then there's another group B, then the temperature drops down, O, B, A, F, G, like that. So our star is a G-type star. Solar constant is the energy what we received at the Earth's distance. That is the solar constant. So it is almost constant. That's why we call it a constant. 1,360 watts per meter square. Inclination to the rotation axis, right? Rotation axis actually inclined to the plane. Overall plane is around 7 degrees. Age is 4.5 billion years old. Now you know that the sun is at the middle stage star, so therefore they can live another 4.5 or 5 billion years. Totally, it's going to be 10 billion years, the estimation, uh, the lifetime. The solar constant is the amount of solar radiation crossing the square centimeter at the Earth's distance from the sun at each second. So that is the definition. So this is very simply you can calculate this. You know the luminosity, and then we are here at the one astronomical unit. Then you can simply calculate how much energy we received L over 45 r squared, and that is going to be that 1,366 watts per meter square. So that is called the solar constant. uh, Chemical content of the sun. The sun is mostly hydrogen. You know that all the stars actually consist of hydrogen mostly. 90% or above that, it's 100 hydrogen. Here is 90% is hydrogen, and then helium, because hydrogen is converted to helium. So the helium content also the second one. So it is 8.8 or maybe like 9%. And then if you go for the other elements, they are very, very small, insignificant amounts are there. Oxygen, carbon, but all these elements are there in the sun. That is the important thing. Sun is a kind of a young star. So it is a population 2 star. So that means the metallicity, the metal content is high. So the sun has a higher metal content. That means the metals are there. If you look at the atmosphere, the solar atmosphere, you can find out all these metals are present, like ferrous, magnesium, silicon, calcium, then the sodium. All these elements are there in a very fractional amounts, very tiny amounts. So that is the chemical content of the sun. Right. Now, we discuss about the solar rotation, right? Now, I just a while ago I show that the sun rotates on its axis around maybe 27 days. Sun's equatorial region rotates maybe 24 days, right? So the polar regions may be 30 days. Why the sun rotation varies along the latitude? Of course, that is because of the it is a gas ball. Since the sun is a gas ball, it does not to rotate rigidly like solid planet. That's obviously clear. A rotation was first detected by the observing the motion of the sunspot by Galileo in 16. You remember what I did it the last presentation. Galileo observed the sunspots through his the very first telescope, right? 1610. So the rotation can be found from different difference in Doppler shift. Galileo actually also estimate the solar rotation using the rotation of the solar, the sunspots basically. The feature what we call the sunspot, I will come to that later. But he observed the sunspot, and then he estimated the solar rotation. So that is the way earlier. But now we can do the solar rotation, we can estimate it very precisely using Doppler shift. So this is basically the rotation. This is animation of sun, and you can see this sunspot actually rotates and just shifting across the disk slowly. You can get the idea about how fast is that. And this is we can use basically to estimate the solar rotation very accurately. This is maybe a kind of experiment we can try out with having some spectrum, right? Now, we have tried this in Arthur C. Clarke Institute, this solar rotation, this method, the Doppler shift method. What we do here, we have a spectrograph. We can take the spectrum of, this is the spectrum we have taken, sample spectrum of sun, right? Uh, Now we can take the spectrum at the center like this at point B, and then we can keep the spectrograph at this edge, the right edge, as well as in the left edge, right? So then when you get the spectrum at the center, that is going to be like this, then we select a one particular absorption line. These are absorption line, you can see here there's a one absorption line here, and these are absorption bands basically, right? But there are weak ones are over here. There's a very prominent absorption line here. So you just look at one absorption line, you take it here at B, and take it the same, look at the same one at A and same one at C. Then they are shifted to the red side as well as to the blue side, because this is going away from you. This right edge is going away from you, the left edge is coming towards you. So then we observe the Doppler shift, Doppler effect, and therefore that Doppler effect makes some shift in the spectral line to the red and the blue side. So therefore we can calculate how much is that delta lambda. Then using the simple equation, V equals C delta lambda over lambda. Lambda means whatever you use the absorption line over here. Delta lambda is the shift. Then you can calculate V, and then of course you can calculate the period as well, the rotation period. So this is very precise one. And actually this is the solar spectrum, right? This is the solar spectrum. These are called comparison spectrums, right? These are comparison spectrums. They are not the solar. This is the middle one, the solar absorption. Now you can see this absorption lines over here, and these are comparison spectrum, which is used to calibrate the solar spectrum. Now we have done these things in our institute. Right now we come to the temperature of the sun, right? Solar atmosphere can be divided into three major parts. Now let's see what are these different areas of the sun. So depending on the temperature, we can divide the solar atmosphere into three groups, what called photosphere, chromosphere, and corona, right? And again, the interior also, we can divide it into three major parts according to the temperature, that is core, radioactive zone, then convection zone. Radioactive zone and convection zone. Then there are three parts also. Outside also three, atmosphere, inside also three parts. So let's see what are these parts. Now, if you look at the cross section of the sun, so this is the photosphere. The photosphere is the one you see usually when you look at the sun through a telescope, through a filter. Then you see a ball, right? A bright ball, a disk kind of thing. So that's what we see. That is the photosphere. So the photosphere is the temperature is around maybe 10,000 to 6,000 K, the range, right? But go to a higher value as well as a lower value in the photosphere. Then, so something above little, above from the photosphere, just go little above the photosphere. Then we have chromosphere. The chromosphere is a 4,000 to 10,000 K, the range. Then we have a corona. Corona means a well away from the sun, right? Well away. When you go beyond the sun, maybe a thousands, not thousands, millions of kilometers even away from the surface of the sun, we call that is the corona. The corona is, you can see here, something strange. The temperature range. It is 100,000 K. So the known physics, we know that if object is very hot, so when you go away from the hot object, so the radiation actually just then spread out radially, then it will drop exponentially, the radiation level or the heat, basically heat as well. So therefore, this is very unusual. We just go away from the sun even. It is more than the surface temperature. The corona temperature is more than surface temperature. Now here, that's why we learn the sun still, although it is very close to us, as well as we know most of the information of the sun, still there are a lot of things yet to be known, right? So this corona heating is still a question completely not understand, but uh, they have people actually given some explanation for this, right? Maybe a fair explanation, so that there's a corona heating process going on actually due to these solar activities, what I'm actually discussing now earlier, again next few slides. So due to these the solar activities, the corona heating is going on. Maybe this corona heating produces this much of temperature outside the sun. So there are some arguments or the discussions going on why the corona is very hot. Or basically, it's more than photosphere and chromosphere. The core, that is where the energy production is going on. Core is 150 million Kelvin. It's a very hot, right? The nuclear reaction takes place there, so it's a very high. And the radiation, the energy produced in the core, it's actually distributed through the radiation zone, right? And that is another part. And then we have a convection zone. Whatever the radiations come out from the sun, so it is through the convection process, it will just release to the space, right? This is convectional current, basically convectional current. The hot gas rises up, then cools down and come back. So then this is going on, the circulating the current in this part of the sun, and then release the energy to the surrounding through the convection zone. So those are the three inner parts as well. So here, usually these are the basically the sizes of these three layers. So the core is maybe up to 25% of the radius, right? core is 25% of the radius, and then be up to maybe 70. Between that 25 to 70, it's going to be that radiation zone, and maybe another 30% is going to be like a convection zone. But you know, these are not really defined, right? Still not really defined, clearly defined. But we know that other than I mean, compared to the other stars, we know very much about the sun, right? So maybe these are up to maybe a 90% correct, but it is very important to know about how the other stars actually, these regions actually divided in percentage wise, how long they are, how big is that. Still, it's very difficult to know. The energy production of the sun is basically the nuclear fusion. So the hydrogen is converted to helium. This is a very complex process. I don't put all these complex equation here. However, it is hydrogen converts to helium, and then the energy release. Then we look at some solar activities, right? So those are the things we are going to look at it in detail. There are a few solar activities I listed here. They are called pleasures, filaments, prominences, solar flares, solar wind, and then sunspots, like that. So basically, we find all these activities in the sun: pleasures, filaments, prominence, solar flares, solar wind, sunspots. So let's look at these things a little bit in detail. What are those? Pleasures means the bright region seen in the solar chromosphere. This is a chromospheric feature. So it is not in the surface of the photosphere, it's little above. So that's a chromospheric feature. Filaments, these are bright regions. I will show you how they look like. Filaments are large regions of very dense coal gas held in place by magnetic fields. They are usually appear long and thin above the chromosphere. This is also a chromospheric feature. Prominences is a elongated structure full of material hundreds of times colder and denser than the surrounding corona. Now let's see what are these features. Now, if you look at this sun in this way, this is not a usual way you look at the sun, right? This is through a certain filter. When you look at through a certain filter, then you can you'll be able to see all these features. Otherwise, you don't see these features. Now here, when you look at in this way, you can see here there are bright spots, right? Very bright spots. So they are identified as pleasures. And then these uh, black like strips like that, or maybe fractures like that, you can see the fracture features, the black fractured features, they are identified as the filaments, right? They are very big. Now you can compare sometimes. Now here the earth is a earth, if you place the earth, that is 109 times you can place it over here, right? Earth. So it is, earth is a small dot like this pointer, right? You can imagine how big is the structure even. It's maybe 1,000 times bigger than the earth, one structure. So these are called filaments. They appeared as dark fractures in the solar chromosphere. The prominences means when you look at the limb of the sun, this is the limb, and then these features actually just upright, or maybe just elongated structure from the above of the photosphere, hanging above. So therefore they identified as prominences. Actually, this is if you look at a little bit bigger, or maybe a magnified image of a prominence. So they are hanging in the surface of the sun like this, but they just lifted above the chromosphere very much, maybe millions of kilometers above the sun surface, and then hanging over here. That's why they are colder than the surface, right? The surface temperature is like, let's say, 5,700 K, but here it's a relatively less low temperature, like maybe 4000 K. So when you look at this feature from with respect to the background of 5700 K, so this they will appear as a dark area. Actually, the filament and the prominences, they are not different, right? They are same. The 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 view, the way you look at it. So when we look at in this angle, that means when you look at directly the solar disk, so we don't see the depth of that. We just see that it is always on the surface. So we identify it as filaments. But when the filament actually just go to the and rotate it over here and then go to the limb, then it will be look like this. It's just hanging, right? So therefore, these areas the temperature is low compared to the surface. So that's why we look at these dark features. So otherwise, they are same activity, but the way you look at it, it's we identify it as a different structure. So this a laboratory demonstration of solar prominence, right? Actually, this is not a solar prominence. Rather, it can say that is a solar flare. So the solar flare with the prominence, if you look at the prominence, this can hang for a long time, like lifetime, maybe a few days, right? It won't change much. Slightly there are changes, but it won't actually erupt it like. So it will hang for some time, like 1 or 2 days, and then slowly disappear. But this feature is kind of a feature like it's just erupting. Basically, some of these prominences can erupt. Sudden eruptions can happen. So then we identify those eruptions as solar flare. This is a kind of a demonstration. It's actually just done it in laboratory to show how does it going on, right? So this is a kind of a think we can think about. This is the way the solar flare can generate. Yeah, there are some videos, a few videos also I have. Let's see, we can check whether we can. I think I have to share it separately for you. Okay, I will stop sharing for a moment. I'll just to make it. Okay, now I will share. I think it's this one. Yes. Okay, can you see the video? Can you see the video?
Yes, sir.
Yes, yes.
Okay.
Yeah, we can see it.
Okay. Now, this is basically some of the video, the images actually taken, very high quality, very high resolution images taken from a space mission. You can see these structures are really big. These are prominences. All of them are prominences, active regions. So that is a one video. It's taken from Soho satellite. Okay, I will show you another one. It's there. Okay, there's another video. Let's look at that also. Okay, now this is how dynamic is the sun. You can see it's these are actually still frames uh, just put into a stream of video, right? Still frames, lot of still frames. You can see the time is going on here. 2003 May 29th they have taken, and 30th as well, right? all these images, close by images taken, and you can see how dynamic is the sun. So this is one activity is going on. There's another one here. It's a dynamic place like a solar flare. This is a flare. So there are a lot of flares actually going on during this time. You can see. So this flare is a very huge flare. It's going on from here. See, can. But some of these features are actually hanging over without changing very much, so they can actually identify as basically the prominences. So, but here it's most of these are solar flares emissions. Okay, right. So we come to the presentation. Okay, I think you can see the presentation now. Right. Okay, here, so the solar flares are huge explosions on the surface of the sun, throwing out massive amount of materials as matter is heated to millions of degrees in few minutes. It can last for the minutes to hours. So the solar flare, it can be actually last long for minutes to hours. Uh, so uh, uh, so then it can produce the solar wind as well. So this flare is an energetic event. Sometimes we call that is a coronal mass ejection, solar flares. They are basically different, right? Coronal mass ejection. So the flares and the coronal mass ejections are the activities which is responsible to heat the corona, basically, right? Because they just throw out a lot of energy, radiation, as well as high energy particles, so then can actually produce heat up the corona, and then these particle events or radiation can just pass through the entire solar system at the even at the end of the solar system. Even some of these energetic particle events can be detected, so they are very strong. So here the sum of these solar winds, we can actually measure the speed of the solar wind, like earlier I said that 500 kilometers per second. So then there's another quantity we use to uh, measure the strength of the solar wind, like a particle density, basically the proton density. How many protons are there just per second, like that, when just passing through the earth. So then these informations are there. If you wish to find out, or if you like to look at these events every day, you can actually go to these websites. One website is actually spaceweather.com. This is a very interesting website. You can find out a lot of information about the solar activities, day-to-day activities. Uh, I don't know whether you can see that. Let's see. Okay, I will show you because that is very interesting to see that website even. Uh, I'll show you that website. Okay, here. Can you see the website? I think. Now, in this website, uh, this is spaceweather.com. So it will give the current condition of the sun. So the solar wind, now the today's solar wind speed, 349.8 kilometers per second. So this is actually I made a mistake over the presentation. There's a proton density, that is protons per cubic centimeter. That is a 4.6 proton per cubic centimeter. That is the density of the solar wind. And then it also just gives some idea about the X-ray solar flares, whether it can actually happen or can predict the solar flares as well. And especially the number of sunspots available today. Basically, the number of sunspots is 25. Today's number of sunspots. So even you can actually enlarge the picture. If you click it, then you can see the sunspots in detail. And the spotless, the days, like the past details about the sunspots, all these things. So you go down little more, so you can find out here the predictions. Now this is very interesting prediction. This is the flare predictions. Flares actually categorized into very strong flares like X class flares, M class flares. So they just say that the possibility of getting an M class or X class flares in the next 24 hours is going to be 1%. So it's a very low uh, prediction right now. So we don't have to worry about, because the sun we don't see any activity right now. So although there are few to 25 sunspots, they are not really active, very small sunspots over here. So then those informations are available. Even you can go down further and then find out a lot of information about the asteroids. So I'll come to that later on. And then yeah, there are some informations you can get it every day. So it's a very interesting website to see. Okay, and then we have another website that is called actually this website is a mission. Right now we know that there are few missions sent by NASA, ESA, and all these people. At the moment the sun is actually observed very close by in 24 hours, very close by this mission, Solar Dynamic Observatory, SDO, Solar Dynamic Observatory. So that is observing throughout the day. So all these information you can get it, all the images you can actually get it and do research. So this is very interesting. Now even if you have some basic idea about the solar activities, especially the undergraduates can actually get this data, because this data is free. These images are freely available. So if you want to do some research on astronomy, this is the way to start, right? So there are a lot of free data sources are available. This is a one. If you look at like if you want to go to like a solar physics or something like that, this is the best way to start. So you just look at these databases and then see what are the data available, what type of data is there, what can you do. You have to find out some research papers. You have to read research papers and find out what they have done from these use data. Then you find out some way to start a project. Like it's very simple, right? So it's very interesting. There are a lot of opportunities available on this area as well. Okay, so here, uh, this is also an image of that, but I have here few images, videos as well. I don't know whether all these things are important for you, but I will try to show you some of these videos. It will take some time to show the videos. Okay, let's see few of them at least. All of these are solar flares. Most okay, I think this is better to see. Okay, so it's a very now you can see here how a solar flare actually generated here. It's slowly triggering here, and you can see it's building up, and then finally blows. You can see it's a huge one. So it's I mean, this is maybe it takes sometimes maybe take 1 day, but the solar flare can actually happens within few minutes. It is like a maybe a few minute event, like a maybe 10 minutes or 15 minutes event. When it start erupting, till just finish within a few minutes. But to trigger it, maybe it takes a few days. Yeah, right. Okay, so then. I think some of these videos not really they are almost safe. This is just for interest. I got all the videos. Okay, that's not working. Come to that later. Okay, now this is yeah, this is worth to see this video here. Now you can see the video. Uh, Now you can see the corona as well. So there are some flares going on here, especially when you look at this is the corona is background, right? It's a the big area right around the sun. You can see here in this point, it's a flare, and what is the importance of this flare? This flare is actually just erupting towards us. So this is our view, actually direct view. So it's actually erupting towards us. So it's a very dangerous, right? This is basically it's coming towards us. Then all these things are directing us. So some flares actually you can see they are just pointing at the other direction. So the effect is minimum, but here the effect is maximum for us. Okay, I think yeah, that's all. Right. So we'll move on to the slides. Right then, yeah. Now let's look at sunspot little bit detail, because these are the events actually just basically triggering everything. Sunspot. Sunspots appear as a dark spots on the surface of the sun. The temperature in the dark center of the sunspot drops to 3700 K. However, it is low than the surface temperature. That's why it just appear or look as a dark area, right, in the sun. So the sunspots are magnetic regions on the sun with the magnetic field strength thousands times of the Earth magnetic field. So these are magnetic activities. Now, almost all the events in the sun, they are magnetic activities. They are basically due to the magnetic changes, the magnetic field. Now let's see how the sunspot appear. So there's a theory produced here or introduced that's called Babcock theory. Most of the magnetic field lines are in the photosphere follow the motion of the photospheric gases, but sun rotates differentially. You remember that I earlier told you that there's a one importance of the differential rotation. It's called differential rotation. Because of that, equatorial parts move faster than the higher latitude. So then what will happen? Now, if you look at the magnetic field exactly just below or the on the surface of the photosphere, because of this differential rotation, they are rotating faster than the polar region. So these magnetic field lines stretched or just tends to move along the equator toward this side, the rotation toward the direction of the rotation. So therefore, the magnetic field lines get distorted, as well as, let's say, it's a stretching toward this side, and finally they are stretched more and more because of this differential rotation, and then sometimes these magnetic field lines will break from the main magnetic field. That means the general magnetic or the main magnetic field lines goes like that. But some of these magnetic field lines actually just break it and then form local magnetic fields. Local magnetic fields, like small magnetic fields around here. That means north-south poles are exactly over here, like here, right, in different places in the sun. So then what will happen, those magnetic field lines also just hanging on the surface, like the field lines go from north to south like that, and they connected from the underneath it, as well as it coming out of the sun surface. So this is the way the plasma is actually lifting. The plasma of the photosphere can lift to the chromosphere, right? By these effects, by these magnetic field lines. So therefore, then uh, all these features, like what I say, that the filaments, the prominences, even the solar flares, actually just produced by this effect. So then you can imagine how this differential rotation is actually important to produce all these solar activities. So these are the different view of a sun. This is a different view of the sun. You can see the sunspots, how they are appeared here. They are very complex structures, right? So basically, most of the sunspot, not most of the sunspot, every sunspot has two polarities, south and north, north-south poles, right? Uh, there are two poles basically, right? So this is a one sunspot over here. Sorry, this is the one sunspot, and there's another sunspot very close by. However, one is north, other one is south pole, right? So the magnetic field lines going like that, and then the magnetic field lines, along the magnetic field lines, the plasma actually lifting over here and then cool down somewhere here. So therefore the temperature drops, and you can see this feature as a prominence, right? And these two footprints basically look like what? They are identified as sunspots. So this is basic idea about how all these features can produce in the sun. Okay, so this is very close by image of the sun. You can see when you look at very close, very high resolution image. Now these are called granules. Granules means actually they are the ones that are like a very small convection holes. These are convection holes. So the convectional loops, right? You can see billions of convectional loops just releasing energy of the produce inside the sun and releasing to the surrounding by this. So when you look at the, I don't have a dynamic picture of this, but they just changing. But all these are there, these small granules are there. So this is a sunspot in detail, right? If you look at it, you can see the magnetic field. You can see there are two regions. Very dark region over here, right? That is called umbra. That means a dark shadow. Umbra means a Latin word. That is a dark shadow. And then called a penumbra, right? Light shadow. So then we almost all the sunspots actually show these two features very clearly. But we have seen some of the sunspots are not really like look like this. But most of the sunspot we can definitely find out an umbra and surrounded by a penumbra, right? Okay, so then we can classify these sunspots also. It's a very nice research work also. Anybody can try out, maybe A-level students can also try out. But anyway, we need to get these pictures. These pictures are available. These sunspot pictures are, the full disk image is available every day. So it's a very good exercise. This can be done by any A-level student even, right? Uh, this is the classification, sunspot classification. First of all, I just go for this one only. Now we assign groups for this sunspot, like by just looking at the shape. Now, if you see like a sunspot like this, so we give A group. We put into that A group, and it is a bipole, and you don't see any penumbral structure. That is going to be a B group. And we have a like a complex one with a set of umbral dots, right? And here there's a penumbral dots as penumbral parts also. So that is going to be C, and like D, E, like that. So these are very complex groups like F, right? So like that we can group, we can assign a group to sunspot in a solar disk. There's another classification called Macintosh classification. This is almost similar to that. You can find out these things in the internet. Then we can find the sunspot number. Now, in the spaceweather.com also, you have seen that today's number is 25. So similarly, we can find out whether we can get the same number of sunspot, at least close to that, with this classification, right? So what is the way to get it? What is the formula? R is equal to K 10G plus F. Actually, K is a constant. It is actually depending on the factor that the location as well as the instrumentation, we have to calibrate it for our instrument like a telescope and the location as well, basically telescope. R is the total number of sunspot. G, G is the sunspot groups, number of groups. Now, the number of group means if you find out there are three groups in available in your disk image, like A, B, C, then G is going to be 3. And then F. F is the number of individual sunspots. Individual sunspot means now here if you look at, I think I have a diagram. Yeah. If you look at this diagram, you have to count all these small dots as much as possible. Those are individual sunspots. F. So then when you put into this equation, you can roughly calculate the number of sunspot available. So for example, maybe you can actually get kind of an image like this and then find out how many sunspots are there. Okay, so this is a very complex sunspot group. Right? I have again a video connection over here. I don't know exactly. Let's see whether it's worth to see. Otherwise, I will skip it. Uh, okay, I think it's a changing sunspot. Yes. Okay, I will skip it for that at the moment because it's just changing the sunspot. Right here, now this act now this the appearing of the sunspot or appearing of all these, basically the sunspot, right? The appearance of the sunspot, it is called the solar activity. It's a solar activity. uh, when the number of sunspot is more and more, then the solar is very active. We call the solar is very active, sun is very active. More number of sunspot means the sun is very active. Less number of sunspot means it's a very low activity period, right? So then we have the statistics from very early. You know that the Galileos also count the number of sunspot every day. So we have the statistics from 16th century up to now. When you put all these number of sunspots, right, every day the number of sunspots, then it is going to be look like this. Right now we have today's sunspot number like that. Now when you look at this distribution, it is not going to be like a just an arbitrary one, or maybe it shows very clear rising and then lowering, rising and lowering. So this rising and lowering, we identify this cycle as a solar activity cycle. So this solar activity cycle is a 11-year cycle. You might know about that, right? So this is 11 year. Every 11 year, the solar activity becomes higher, the highest. Actually, then it will go down again, going to be maximum, and then again minimum like that after every 11 years. But apart from that, the 11-year cycle, you can see some fluctuations over here. So this is a period of 50 years called Manda minimum. The activity of the sun is very low. Here again another minimum we occurred. We see here. Then that is called the Dalton minimum. So after that we don't see such a drop like that, and we see a very highest value or highest activity period in 1950s. That is the highest period at the moment recorded recently. And now we are here. We are now going on. Just we just finished the 24th the solar activity cycle, right? Now it's a very interesting thing you can see here from 19th or maybe let's say from 21st cycle. It is seem to be slightly dropping, right? The maximum number of sunspots, it's dropping. The maximum activity is dropping from 21st 21 to 24. So now we just started recently. They announced that the 25th cycle has started, and then the number of sunspots getting increasing. Right now it's 25. Then because the beginning of this year and the last year, the most of the days are no sunspots, zero sunspots. But now we observe the sum of the sunspots, that means exactly the 25th cycle has started. But we don't know when it is going to be, how it is going to be. So we have to wait until maybe 2024 or 25 to see the maximum of this cycle. And they have predicted that the weakening trend, so there's a going to be weakening. We don't know whether this is going to be another minimum, right? It's very interesting to see, but we have to wait for a few years because these cycles are very long period cycles. Okay, so then the reason of this the activity cycle of 11 year is basically again it's due to the magnetic cycle, magnetic activity. The 22-year magnetic cycle, that means every 22 years, the magnetic field, the polarity will change. It's a kind of a very unusual or maybe unbelievable thing, right? The polarity is changing, like a north-south change. So this magnetic, the reverse, the reversing of this magnetic field is the cause that is actually causing the activity of the sun or the sunspot cycle basically. But however, it is actually changing every 22 years. So the half of that is exactly 11 years. Now we see the 11-year sunspot cycle. So this is the magnetic reversal plot given by the NASA mission. So you can see every sunspot now. These the blue and the yellow shows reverse polarity, like south and north, right? Reverse polarity, and every 22 years, so they will appear as the same, like here and here, right? After 22, almost 22 years, like that. Again, blue here and then. So these sunspots actually just changing. These are the sunspots, right? The distribution of sunspot, and the sunspot actually get reverse polarity right here. So here it's a reverse. So then the lower sunspot actually gets south pole, maybe north pole here. This is north pole and the south pole. So they are reversing. And again we get the same after 22 years. But in every half of the year, half of the period of that, we get the maximum activity period. So then they found that there's another relationship. Uh, Once the activity started, like right now, usually the sunspot appears in the higher latitudes like 30 to 30 degrees plus and 30 degrees minus. But, but when it becomes maximum, they are getting closer and closer, just appearing closer to the equator mostly. So this is like a very nice arrangement, like a butterfly, right? So they identified as a butterfly, named as a butterfly diagram. So that is about the solar activity cycle and all. So I will go through these with, since I have taken almost 1 hour right now. I'll just go briefly about this. The effects on Earth, right? One effect of the solar wind is, or the magnetic activity is aurora, right? Charged particles motion in Earth's magnetic field. You know, these charged particles actually just reaching the Earth, as well as they can affect the Earth, right, in a different way. One effect we can visualize it as aurora, right? The appearances of aurora, that is a northern light. Actually, this is artistic view that how the solar event, the solar wind, or maybe a emission of solar flare or coronal mass ejection that compress the Earth's magnetic field, and then finally it get affected by the Earth, and we feel also sometimes. So, however, because of this radiation, there are two regions also identified around the Earth, what called the Van Allen radiation belts, outer radiation belt and the inner radiation belts. They are ranging from 640 kilometers to 58,000 kilometers. The lowest one, the inner radiation belt, is you can find out in 640 kilometer, and the outer belt actually just go up to 58,000 kilometers. So these are radiation belts produced by the solar wind, solar activity. When you this actual diagram I put it to show that these solar activities can affect missions going on. We can see beyond, and then International Space Station close orbit, right? It is a 400 kilometers above, and it's going on very quickly. And here the Van Allen radiation belt, right? Here the Van Allen radiation belt, and this is the outer radiation belt. Fortunately, all the low Earth orbits are inside the Van Allen radiation belt, in a belt. Hubble Space Telescope is also inside that. But here, the GPS satellites, all these are, however, little away from, and even the geostationary orbit is the most highest, or the uh, furthest orbit is 36,000 kilometers away from now. Okay. And this is how we get these radiation, the charged particles to the atmosphere. So though they cannot actually come directly towards the earth, right? Fortunately they are not penetrating towards the equator region of that, because of the protection shield of the earth's magnetic field, very high magnetic field. But they can actually trap the magnetic field lines and can enter or get into that earth from the north and south pole. So when they get into that, we see this natural phenomena, what you call aurora, northern lights, like that. Okay, beautiful sky glowing. That the night sky is glowing with the different colors. Why these different colors? It is due to these charged particles can excite, they are exciting the earth atmospheric gases. Basically we have oxygen, nitrogen and oxygen. If you look at the emission spectrum of atomic oxygen, so we can see very strong emission line in green, and then few lines in red, but very weak lines, or almost no lines in the blue region. So therefore, if the aurora is something look like red and green, so that is going to be responsible by the atomic oxygen, basically oxygen excitations, right? And if you look at the nitrogen spectrum, the emission spectrum, nitrogen shows most of the line in the red as well as in blue. So therefore, the combination comes look like a pink or maybe a purple color. So basically, it's due to maybe nitrogen. Okay. Right. Now we can observe the sun, observation in the white light. Now these are the special filters we made out in Arthur C. Clarke Institute. This is a special filter designed for the solar observation. It's a very safety filter, no problem at all. You can look at the sun for any time, right, without any problem. So when you look at the sun in that filter, it's a white light. So these are the images taken from our telescope. And then we can take another image, a different type of image, through different filters. So the different filter give different feature extractions, you can get it, right? So this is solar observation in H alpha line. You know, H alpha, hydrogen alpha, Balmer line series, H alpha, 6560 angstroms. So this filter is a narrow band filter which is designed to observe only, filter this wavelength or the narrow wavelength band, and cut off all the other wavelengths. So it's a very this is a very expensive filter anyway. So we have this filter also. And when we look at that, the red color, all the images or prominences, filaments, and then activities uh, can be seen through the H alpha filter, right? So therefore, this is what we have taken the H alpha images. Uh, they are not very high resolution. Anyway, it's a small telescope. But this is not, this is changed, right? This is already processed image. This is not the color. This is the actual color, right, of H alpha, red line. This is also a processed image, but I just wanted to show that the color change, because this is a filament. We got a filament structure over here and the prominences over here, as well as granules also. You can slightly see granules with a small telescope. These are some of the activities we are carrying out in our institute. The solar observation we are doing some research on solar observations, right? Apart from that, the visible images, we are now carrying another research area called E-Callisto program. That means we observe the solar radio burst, the radio emission of the sun. The solar flares emits entire electromagnetic spectrum, so including the radio region, radio emissions also. The radio window we can actually observe through this special program called eCallisto. We have a station in our the Clark Institute. This is a worldwide program. It is actually it is conducted by Institute of Astronomy Switzerland, and even these receivers actually designed by themselves. And we got the receiver, but we designed this antenna to receive these radio signals at ACCIMT. So this program is going on, and this data is available. This is the first result we observe, a solar flare activity. This is the solar flare, right? You can see the solar flare. It's just recorded like this, but I think the next one I will show you. Uh, this is how the flare goes on with the time. This is a frequency. It's a frequency sweeping event. It's a frequency is going from 400 megahertz to 150 megahertz sweep with the time. This is the first flare activity. So with this data, you can study. There are a lot of opportunities created over here. I mean, anybody can come and then work, use this data, this free data, and then they can actually do their research based on this data. Okay, so then how do you start observing the sun? Uh, don't look at the sun with the directly with the unaided optical device, right? So the solar observation has to be done very carefully, right, with the expert people, kind of an experts in that area. Otherwise, a slight mistake can actually go a complete blindness. So don't use any optical device to observe the sun without a filter, right? So there are some few ways to observe it carefully. If you have a binocular, you can close the one end of the binocular and then open the other end and then project it to a screen. Especially the university students, if you have a event, then you can organize an event, but carefully, just try to conduct it carefully, the solar observations, right? You can project always to the screen, but be careful that also, because the heat of the sun is very much, so that can actually damage the eyepieces of these also, right? This is a one arrangement we have used it, projections, right? The projections method, basically. This is one, you remember that there we had the solar eclipses, right? Annual eclipses, we had it 2019 in December. So we use this setup to observe the sun for an experiment. This is the setup with filters and all. Okay, so that's about it. I think I will finish the presentation with this. And of course, the effect of solar activity on the Earth, climate, and communication. Now, these are the effects. This is a one effect called polar cap absorption event. The solar protons can penetrate into the Earth's magnetosphere near the magnetic poles. Shortwave radio waves at a relatively high frequency in absorbed by the increased particles. So that means basically the solar cap absorption event can absorb the solar radiation, the high frequencies, right? Basically the radio waves. You know that it can completely black out the radio communication, because you know that the ionosphere we use for the radio communication, the radio signals actually then reflected by the ionosphere, right? This ionosphere is almost uniform, but during a solar activity, this uniformity will lose, and then the ionosphere get actually disturbed. So therefore, the disturbances can actually just make a anomalous reflection of the road radio waves. So you don't actually get the radio signals right properly. So that kind of communication blackout can happen, right? And the solar wind disable the satellites. Of course, they are very high energetic particles and radiation. It can destroy the sensitive electronics, especially the solar flare, the solar cells and all, right, can damage it. So then it will drop the lifetime of the mission. And then the solar flares affect air pilots and astronauts. Very dangerous, right? The astronauts and especially the pilots just going through the polar region, right? So they are also get affected very much on the solar radiation, because the polar regions directly penetrate the charged particles. So therefore, they are exposed to the higher radiation than the other people. And this is what I actually explained, that the total power blackout in Canada in 1989. So it's due to a solar geomagnetic storm, I mean, solar event. It's produced a geomagnetic storm, fine. Then it just produce some unusual voltages and generate currents in the power lines. And then those fuse actually just blow, and for a 9 or maybe 8 hours, the total power blackout was actually experienced in Canada in 1989. So this kind of events was there in history also, due to the solar activities. So I think with that, I will just give some brief understanding about the importance of sun and the activities going on while we study the sun. So I think, yeah, it's the end of the presentation. It took a long time. It's open for the questions. If I know something, I will explain to you. Okay, thank you.
So thank you, sir. Now it's time for the Q&A session. So if you have any questions regarding today's session, now it's time for ask them.
Hello, Janaka. This is Sivakumar. Can you hear me?
Yes, yes, yes,
Yeah,
bro.
yeah.
I can hear.
Wonderful presentation, very lovely, and it's
Thank
like very well connected from the beginning to end.
you.
Um,
Thank you.
yeah, very good information. I mean, really enjoyed. One quick question about this: the periodicity you had in this formation of the spots, right?
Yeah, yeah.
Do we have similar for the flares, or is it something very random?
Uh, it's not really, because the flares can actually, basically the flares also get maximized with the activity of
Okay,
the sunspots. The sunspot is the one we actually clearly measured it, because
okay,
the solar flares, basically we cannot measure it, because some of the solar flares are not directing towards us, and some of them are going slide away. But even the sunspot, even the same way, but at least sunspot can actually just stay for a 1 or 2 days. There
okay.
are some sunspots actually disappeared very quickly. So
Yeah.
therefore, that is the very clear way to measure the activity. uh, the,
Okay. Yeah,
the
yeah, yeah.
solar flare
Sure.
can actually, it's a very unpredictable, and even
Yeah,
some unknown flares over just happening in the behind the sun. We don't have any facility to look at the sun, the behind the sun. So what's
okay,
going on? So therefore, but however, with the activity, the maximizing the activity, the solar flares also get maximized. But
okay,
we don't actually say in terms of solar flares. We always
okay.
say, yeah, that in
In terms
terms of
of, yeah,
sunspot. Yes.
yeah. Why I asked that, because I mean, when these the space station, they go for spacewalk and all,
Yeah.
do they have any idea they will be? I mean, is there kind of a weather prediction like thing going on, or how do they? Is a
Yes.
risky thing?
Yeah, exactly. That's another that's what I just pointed out from the beginning, how important is looking at these activities. Still, most of these are not completely known.
Yeah,
So, I mean, we cannot predict a solar flare, basically. So we have actually just produced some models to predict it. With
yeah,
that, the spaceweather.com also, they predicted like a 1% or 2% chance of this particular sunspot or maybe active region can actually erupt it right now.
yeah.
But even it is like a prediction. So sometimes they not just maybe erupt it, or maybe erupt it unusually or
Yeah,
unpredictably. So it is very dangerous at the
yeah.
moment, right? We
Right.
don't know exactly. but some way they have developed physics or just models to predict it now based on these magnetic activities. Basically they measure the magnetic field of the sunspot or the active region. So they
Mm.
said this is kind of a magnetic field, like it's a not a stable magnetic field. The
Okay.
stability they can measure it. So based on then they predicted, okay, this is going to be erupted maybe soon, because it is an unstable magnetic field going on. So kind of way, but
Yeah.
still
Yeah.
not completely known when it is going to erupt.
Right. All right, thank you very much. And one quick comment about very encouraging words that you even say. I mean, even an A-level student can do, this kind of study or something that is very encouraging. So
Yes.
I'm sure there will be a lot of our students, I mean, interested in sharing the data and maybe starting a project or something like that. So even I think we have to open up some kind of a discussion on that to see how easily or maybe how you can or maybe a mechanism to guide them to start something, they are interested in doing some research or something. Just a comment. I mean, we
Yeah.
have, it's very up in the air, but we can work it out later on,
Yeah.
maybe once things are established.
Yes.
And thank you very much. It's a very lovely, very nice lecture, very informative, and I enjoyed a lot.
Okay.
Thanks. Huh?
Thank you. Thank you.
Okay, okay.
There's a question in the chat section. Mr.
Yeah, yes. Okay, I'll just yes, about the sun's magnetic field flipping every 11 years. Why does this happens? And is it similar to Earth's magnetic field flipping, which only happens every couple of 100,000 years? Yes, actually, I wanted to point it out that I missed it. Uh, why does this happen and it is similar to the Earth? Actually, I am not a position to answer that question. Why does it happen? uh, with that period of 22 years, it is a kind of a, I don't know how to say that. And still going on. I think investigations are going on. Maybe some sort of dynamics inside the sun. Uh, Due to that, the magnetic field is flipping. uh, I am not. I cannot actually get a very clear or maybe a detailed answer for that. Uh, Even that is true that Earth magnetic field also flipping, but it takes thousands of years, right? uh, Basically it's maybe because of the magnetic field generated by the core, right? The rotation of the liquid core. So this kind of changes of the liquid core, kind of a change with the time. So it can actually just change the direction of the magnetic field or the polarity of the magnetic field. Uh, uh, that is true. Earth's magnetic field also flip, but we don't have to worry about that. You know that the one thing I can say that the flipping of the Earth magnetic field is not going to be very good news for us, right? So it is going to be really, really a different situation, a kind of a weird situation we can actually see when it is going to flip it. At the moment, it's no problem because it's a stable, and they found that it will just take long time, thousands of years to flip it. However, it is not like frequent as the sun. So that's the thing I can tell you. But if you maybe want, you can find out a little more on that. Just looking at it in detail, maybe some research papers have published about how the sun's magnetic field actually flip and what is going inside that. Still, the information is very low, and the discovery is still going on, research going on to find out the reasons for these flipping and all. I hope that I answered the question in some certain way. Any questions about further? Yes, there's another one appeared. Sir, how to join the Adassuriya Clark Institute? Are there postgraduate degrees in Adassuriya Clark Institute? Uh, at the moment, we are doing undergraduate research only. There's no postgraduate research going on, but hopefully we are going to start the postgraduate research, and we are going to supervise the postgraduate research as well. At the moment, we are doing the undergraduate research supervision. So you can actually join with the Arthur C. Clarke Institute for your undergraduate research. So now some of you have already done it from your department. So that is available. Those opportunities are available. Some the research areas we have discussed now here. This is a one research area, but one thing I have to tell you now, we have very limited resources. Like a human resource is very limited. Now with me, only two other scientists are working over here. So then even you know that honestly, when you going to be like a very specific in a subject, you can't actually go to another subject, and then you can't supervise that one. Even maybe at some certain level you can actually supervise. Maybe I can supervise even. Now my field is slightly different right now, because I'm actually involving in astroseismology. So this facility is available. Now we have started some research opportunities. We have given some opportunities too, but when you come to that, we can give some basic guidelines to a research, and then you have to find out most of the things behind this. So at the moment, because you know that Sri Lanka now, we don't have a very big capacity in this astronomy, still actually developing very slowly. So therefore, those limitations are there. But with that limitation, even we would like to help you. If you would like to do some research on solar physics or maybe some other area, we would like to help. We would like to give our best to you if you want.
Mr. Janaka,
Yes.
you mentioned that the corona has a high temperature than that of the photosphere.
Yes. Yes.
This problem also I had. I could not understand. Is there a simple mechanism for that? Uh,
Uh, yes, Dr. Anok, I think the basic understanding is the corona heating by the solar uh, energetic events, the solar flares, and then the coronal mass ejection, CMEs. So they can actually produce it, and there's so much of energy just released to the surrounding. So that energy just excite basically the close atmosphere of the sun can actually just energize the close atmosphere, and then it will produce that much of temperature in the corona. So that is at the moment what I know, that kind of explanation, basically due to that solar activities, basically solar flares and the coronal mass ejections uh, can produce some energy, and then that can actually heat in the corona. So that is what I understand at the moment.
Thank you. Thank you.
Mr. Janaka, one comment. I'm Varuni.
Okay.
And just a comment. Thank you for the nice presentation. And in line with one of the students' question about postgraduate research,
Yeah.
we can suggest you one thing. There's a student who would like to do a MPhil or PhD, a postgraduate degree.
Mhm.
They can register at Postgraduate Institute of Science, University of Peradeniya, and have a supervisor from the Arthur C. Clarke Center.
Yes.
And probably, I mean, this is how the National Institute of Fundamental Studies, they carry out the postgraduate. I mean, they are also not offering postgraduate degrees currently, but there are supervisors and students also working at NIFS. But then the students are registered at PGIS or any other PG institute in Sri Lanka. So if there are like
Yes.
human resources.
Yes,
That is
actually, that
that can.
practice also we carried out with the Columbia University at the
Okay.
moment. Yes. So the Columbia University, they are some of now recently we have done a few postgraduate degrees
Uh-huh.
with the collaboration of that. So from our side, we are supervising. We assign a supervisor from our side. Usually, they registered in Columbia University. It's possible. Yeah, that is the way. Exactly.
Mhm.
That's what you say. Yeah, that is possible.
So thank you everyone. So to conclude today's session, I would like to invite Miss H.M. Gautami to deliver the vote of thanks.
Speaker, Mr. Janaka Adassuriya, Senior Research Scientist at Arthur C. Clarke Institute. So, thank you very much, sir, for being here to enlighten us with knowledge despite your busy schedule. Next, I would like to thank the head of business department, Dr. Varun Senimjan, and your senior treasurer, Janaka, for guiding and encouraging us throughout. Thank you very much, sir, for your support. Then, I would like to thank all the lecturers and all the demonstrators for their presence here. Also, I would like to thank the President of the Astronomical Institute and the committee for success. Last but not least, I would like to thank all of you for the.
So with that, we'll be concluding today's event till we meet next time. So it's goodbye from us. Thank you.
Okay. Good night. Goodbye for that.